Hello everyone. So in this pre-lecture tutorial we're going to wrap up chapter 7 by relating the molecular formula of a compound to the empirical formula of a compound. And so we learned in the last section of chapter 7 that the empirical formula is that formula of a compound that relates the simplest whole number ratio of elements within that compound. Well, the molecular formula, instead of giving us the simplest whole number ratio, it actually gives us the true or actual whole number ratio of elements within the compound. So for example, I have a few examples here underneath this definition. For glucose, the actual or molecular formula is C6H12O6. Now again, as we learned in the last section, I can actually reduce that by a factor of 6 to get CH2O. CH2O is the empirical formula. Okay, I can do the same thing for hydrogen peroxide. Again, if I have hydrogen peroxide's true formula in front of me, that formula is H2O2 because there are 2 hydrogen atoms and 2 oxygen atoms in each molecule of hydrogen peroxide. But that common factor of 2 can be divided out from each subscript to give me HO. And that would be the empirical formula of hydrogen peroxide, whereas H2O2 would be the molecular formula. However, if we take a look at a compound like water, basically the ratio of hydrogen to oxygen is 2 to 1. And that already is the simplest whole number ratio for the elements in water, and it also happens to be the actual whole number ratio of elements in water. And so water is one of those compounds that actually has the same molecular formula and empirical formula. Those 2 formulas are the same for water. And so there are those compounds that have the same molecular and empirical formula. So I guess the next question would be, well, how will I find a molecular formula if I'm asked for it? Well, there was already an item in the application activity related to empirical formulas that touched on this, but I'll go ahead and review that procedure. In some instances, you might be given the empirical formula outright. So for example, here, I'm being told that I have a compound and its empirical formula is CH. But the molar mass for the compound is 78 AMU, or if you recall, we can also refer to that as 78 grams per mole. And so they want me to find the molecular formula. And the way that I do that is I'm going to compare the molar mass for the compound to the molar mass of the empirical formula. So I'm going to determine the molar mass of the empirical formula. And so if you recall, carbon's molar mass is 12.01 grams per mole. Hydrogen's molar mass is 1.008 grams per mole. So if I add this up, I get 13.018 grams per mole, or if I'm going to use 4 significant figures for this molar mass, that would be 13.02 grams per mole as my molar mass of CH. Okay, I'm going to take 78 grams per mole and divide that by 13.02 grams per mole. So I'm going to take the molar mass of the compound and divide by the molar mass of the empirical formula. If I do that, then I get a factor of 6. So what that means is that each subscript, which happens to be 1 understood for this particular formula, but each subscript has to be multiplied by 6. And so that would make my molecular formula C6H6. Okay, but what if they don't give you the empirical formula outright and you have to find it? Well, the good news is we already have some idea of how to find an empirical formula. And so we would just go ahead and use our procedures from the last section to find the empirical formula, and then do the comparison of molar masses once I have the empirical formula in hand. So here I'm told that I have a compound that's 80% carbon and 20% hydrogen, and it has a molar mass of 30 grams. And they want me to find both the empirical and the molecular formulas. And so what I can do is, again, I'm going to assume a 100-gram sample. Okay, and so that means I'm starting with 80.0 grams of carbon. I'm going to change these grams of carbon to moles of carbon by dividing by the molar mass of carbon. And if I do that, if I take 80 and divide by 12.01, I get 6.66 moles of carbon. And then I'm going to do the same to hydrogen. So again, assuming a 100-gram sample, 20% hydrogen would be 20 grams of hydrogen. I'm going to divide that out by 1.008 grams of hydrogen for every 1 mole of hydrogen. So if I divide that out, 20.0 divided by 1.008, I get 19.8 moles of hydrogen. From here, I'm going to divide by the smaller of my two results. So 6.66 divided by 6.66 is 1. 19.8 divided by 6.66 is 3. And so that means that my empirical formula is CH3. But I'm not done yet because I still have to find the molecular formula. And so what I'm going to do is I'm going to find the molar mass of CH3. So that's 1 carbon, that's 12.01 grams per mole, 3 hydrogens, so that's 3 times 1.008 grams per mole. And if I add that up, what I'm going to get is something close to 15 grams per mole. It ends up being 15.02 grams per mole. So I'm going to take this molar mass and that molar mass and find the factor difference between them. So that would be 30.0 grams per mole divided by 15.02 grams per mole. That means that these two formulas, the empirical formula and the molecular formula, are related by a factor of 2. So to get the molecular formula, I'm going to have to take the coefficients in CH3 and multiply them each by 2. So if I do that, that would mean I would get C2H6, and that would be my molecular formula, and CH3 is my empirical formula for this compound in this example problem. So go ahead and try the follow-up assignment where you reinforce these same concepts. Again, if there are any further questions regarding empirical formulas or molecular formulas, go ahead and send me an email. Otherwise, we'll speak in class. All right, have a good night.